Right, it's now time to look at reference architectures for certain types of cloud applications. Obviously, we'll look at very common types that you usually encounter. Uh, cloud applications are usually multi-tier, just like web applications. So there are multiple tiers, and normally a three-tier architecture is usual for web applications. Right, so we are talking more or less of that. For web applications, you usually have a presentation tier. You have the the the, the application tier and the data tier. Or rather, or sometimes the application tier is referred to as the business logic tier. So a three-tier architecture is usually common. So in you will see something similar but slightly different for cloud applications. So what is important rather to note is that there are various deployment architecture alternatives, which are suitable for different types of applications. So you need to be able to choose these carefully. So our focus is basically on the right deployment architectures, which ensure that the cloud application meets specified performance requirements, as we have discussed already. So in this section, we focus on referent architectures for different types of multi-tier cloud applications. Um, right, let's proceed to look at the first one, especially e-commerce. E-commerce, a large number of even web applications are for e-commerce. The same with cloud applications. A large number of these are e-commerce cloud applications. Right, these have got various tiers for deployment purposes, and these are illustrated in this diagram. You have the application tier, which of course is the is a one or more application servers with minimum two to avoid single points of failure. In other words, you have two application servers that are identical or that are clones of each other. Right. So what is important for this tier is that where in order to handle huge workloads, like millions of people accessing that website, you should consider auto scaling. We have already discussed the concept of elasticity or even scaling. So scaling is where you are increasing the number of resources in response to high demand. Right. So auto scaling configuration might be useful where resources are increased and so automatically. So avoid lag during auto scaling as well. Make sure that you don't disrupt users. There is also a database tier, which include master database instance and multiple slaves. Yeah, you have a master and several slaves. The master usually handles write and slaves read requests to improve throughput due to normally high number of read requests. So the regular database snapshots are also important for the database tier. So you then have, of course, the storage tier might be more or less an archive. So notice that we have a load balancing tier. We have looked at load balancing, where you have a load balancer, and with associated with the load balancer, of course, is auto scaling, because especially if you consider an elastic load balancer, which is also capable of reducing the number of servers or triggering the reduction of the number of servers. In that case, you definitely need load balancing to work together with auto scaling to ensure that if the load is too much for the existing number of servers, you can auto scale, you can increase the number of servers and also reduce them. So you end up having an elastic load balancer capable of doing that. So this architecture itself, if you look at it the way it is, it may not really be the right one. So if you look at load balancing in this diagram, you also load balancer one, load balancer two, because one load balancer may also be overloaded. Who balances the load of the load balancer? So you could have a load balancer for load balancers, something like that. But there is a very interesting solution in the industrial presentation that we got from Dietrich, who is a former student of Massey, where he is addressing the challenge where we need a load balancer for the load balancer. They have come up with a new way that really solves that problem, because whatever load applies to the load balancer, it also applies to the application tier, which means although we put a load balancer in there to assist with balancing the load for the application level, it may be overloaded, which basically means we need to have a load balancer for a load balancer, which is not which creates some kind of a vicious circle, so if so, in a way, you can critique this architecture based on that, to say, okay, we may in ordinary applications, usually the load balancer works, but there are exceptional situations where the load balancer itself may have too much load, to the extent that it also needs a load balancer, which then create that vicious circle I'm talking about. So listen to that seminar. You find it on this topics website on Stream, where we have put links to that presentation. Right. Now let's look at another type of architecture for what is called content delivery cloud applications. Content delivery applications use what we call content delivery networks, which are global networks of edge locations, which are used to speed up delivery of static content, such as videos and images. Right. Of course, typical examples of content delivery network is the YouTube network. YouTube network of servers around the world. Their main purpose is to deliver videos. And audio, of course. Once you create a video, you don't edit it, isn't it? You only read it. People only play a video many times. Thousands of people trying to play one video, and there is very little changes that the creator needs to do to the content once it has been uploaded. So in that case, you need a dedicated, optimized network which is meant to deliver the content. I'm sure you have other examples like the music apps. They are cloud-based applications which are in the class of content delivery networks, cloud applications rather. So the content delivery networks have 8 components which are shown in this diagram on this slide. The first one is the content provider. This is the entity delivering the content. In YouTube, obviously, they are YouTubers. Then authorization. The content provider gives the content delivery network provider permission to deliver the content. Once you upload it to YouTube, you are giving YouTube or Google the authorization to deliver it. And also, the content provider demands performance analytics from the content delivery network provider in order for them to evaluate the quality of the provider service and have access to other relevant data. Right. Of course, if you create a video on YouTube, you get a number of statistics. How many people are watching it? How many are watching right up to the end? How many are not watching right up to the end, and so on, so on. So reporting is very important. Then of course you have the source. The content provider sends a copy of the content, right, from the source, right. Then you obviously have the content itself, which is the digital information created or licensed for distribution. And then the request is where a user requests the content from the provider to view or even to download and store locally. That's the request. It comes from the user. And obviously we have delivery that is performed where the CDN delivers the content to the user. The CDN being, of course, the content delivery network. Of course, the user is the entity requesting the user from the content provider. So you have a complete dedicated massive infrastructure for this. Imagine how many videos are stored on YouTube, and so there is a complete network optimized to deliver this content. Right. Normally, a content delivery network has got an architecture that consists of nodes. There are basically 4 types of nodes. You have the delivery node that serves. This is just a server that contains the content either as a cache or the original, right? And the diagram here shows the 4 nodes and how they are connecting to each other. The storage node, of course, is the primary purpose for storing copies of the original data, and the origin node, these are the main sources of the content that enable content distribution across the entire network. And then the control node, this primary purpose is hosting, management, routing, monitoring of the content delivery network. So of course they do interact with each other to perform the functions. Notice that delivery nodes are supposed to be closer to the users. Of course, most networks are push content delivery networks, which means the provider has to upload the content. Yeah, that's a disadvantage in a way. Whereas it's also possible to have pull CDNs. They automatically demand content from the provider rather than waiting and allowing the user to upload. Now the general discontent for all content delivery networks is that when a user first accesses the content, the speed is usually the same as the original speed, because optimization has not yet been done. But Amazon does certain optimizations on the file that you upload. Yes, I say Amazon, but I meant to say YouTube, which is Google. If you upload a video, they have some time when they are possibly optimizing that file, and it says, okay, it will be available soon for download, but wait, we are still processing it. So it means they do a little bit of optimization to allow that. But in general, delivery nodes are meant to be near users, and they tend to cache. And sometimes when you access a video, it's not necessarily in the local delivery node. It has to request from the original server. So it takes quite a while to do that. But the next time you access it, it's already there near you. So you can always play it faster. Right. So this is the general architecture of content delivery network. It's not very different from the e-commerce architecture. You will notice that there is a load balancing tier, there's application tier, then there's a database tier, and after that there is, of course, storage tier. Of course, you can have content delivery as well that allow content to be delivered directly from the storage tier. In the storage tier, you may also have a non-relational database for storing credentials like login information and so on. And so there's only an extra element for storage tier, but the rest of the architecture is similar to e-commerce architecture. Right, now let's look at compute-intensive cloud applications. Compute-intensive applications work in a slightly different way. So when we say compute-intensive, they require a lot of computation. This includes data analytics, because you need to analyze the data. Also, when you have media content and you want that to be transcoded to another media, it takes a while. Even creating this video, I am creating snippet clips of this video, and when I want to create one video file, which I have stopped doing for this course because I like the idea of small videos. I don't know whether you guys like it, but you can of course download each of the video and combine them into one, and if you do that, it will take a long time on your computer. So that's because it's compute intensive. So media transcoding is another area which can take a while to perform, even for the cloud. So this deployment architecture includes a website, it includes an app, it includes storage, computing, and analytics, and database tier as well. Right. So it's fairly more than just if you compare it to the it includes more, similar to the e-commerce one, but slightly different. Then there is an analytics tier which does distributed batch processing, and it can include frameworks such as Hadoop, which can perform MapReduce algorithms, and there are other algorithms for batch processing as well, but MapReduce is one of them. Then there is a data analysis jobs that are supposed to be handled by the server, and then of course you want to run algorithms such as MapReduce as well. Of course, jobs are usually placed in a queue, and completed jobs with analyzed data are presented to the application at a later time after they've been completed. Right. In some applications, you can actually upload. After you upload, some processing is done to that, and sometimes it takes long. That's why the jobs are supposed to be queued. So that's the architecture for compute-intensive application. Notice that you don't always have to have MapReduce. There are other algorithms that could be useful there, but MapReduce is quite popular. There are for batch processing. Right. We all these architectures are basically, we mentioned, they are deployment architectures. Deployment is simply, making these available in the cloud for users to access these apps. There are quite a number of deployment tools that are available, and this table on this slide gives you a few of them. There is what is called Flexera Cloud Management Platform, which allow you to design, deploy, and manage cloud applications, right, across multiple clouds. In other words, you can put some components in Google Cloud, others in all that, and then link them via some kind of communication. Then you have what is called Scala. This provides tools to automate the management of servers, monitor servers, and replace servers that fail, and provide auto-scaling and backups. That's a very interesting tool. It's quite comprehensive. Then there is the Bunny Shell, which is a managed cloud automation software as a service solution that lets you launch and provision, deploy, monitor, scale, and maintain security. So it's security oriented. Then there is Apache Cloud Stack. This is basically designed to deploy, manage large networks of virtual machines as a highly available, highly scalable infrastructure as a service cloud platform. So Cloud Stack is more like, you're building your own cloud, especially for creating virtual machines and that. So with that, we end section 3. In section 4, we look at database choices, and that will be our last section.